Welcome back. Last episode we learned undetermined coefficients, a fast way to find a particular solution by guessing its form. But that speed came with a strict condition. The forcing term had to be a polynomial, an exponential, or a sine or cosine, a function whose shape you could anticipate. The instant the forcing is something like secant x, or tangent x, or the natural log of x, the guessing strategy falls apart, because differentiating those functions just keeps spawning new shapes you would have to guess all over again. Today we build the method that has no such restriction, variation of parameters. It works for any continuous forcing term whatsoever. It is built directly from the two homogeneous solutions and a determinant called the Wronskian. The price is that you have to evaluate a couple of integrals, and sometimes those integrals are genuinely hard, but the method never fails to set up. When nothing else works, this is the tool you reach for. Before the idea, a checklist of what you must already have. Variation of parameters does not find the homogeneous solution for you. It assumes you already have it. So step 0 is to solve the homogeneous equation and get the two independent solutions, y1 and y2. For a constant coefficient equation, that is the characteristic equation method from the last few episodes. Once you have y1 and y2, the full answer has the usual shape. The homogeneous part c1y, 1 plus c2y2, plus the particular part we are about to build. One more crucial setup step that trips people up. The equation must be in standard form, meaning you divide everything through so the coefficient of y double prime is exactly 1. The forcing term g that appears in all our formulas is the right-hand side after that division. If you forget to divide, every coefficient in the answer comes out wrong. Standard form first, then the homogeneous solutions, then variation of parameters. Here is the bold idea, and it is due to Lagrange. The homogeneous solution is c1 times y1 plus c2 times y2, where y1 and y2 are the two independent solutions and c1 and c2 are constants. Variation of parameters says, what if we let those constants vary? What if we replace c1 and c2 by unknown functions u1 of x and u2 of x? So we look for a particular solution of the form u1 times y1 plus u2 times y2, with u1 and u2 to be determined. Now we have two unknown functions, but the differential equation is only one equation, so we are free to impose one extra condition of our choosing. The clever choice, the one that makes the whole method work, is to demand that u1 prime times y1 plus u2 prime times y2 equals 0. That single condition wipes out a pile of messy terms the moment we start differentiating, and it leaves us with a clean system. Let's turn the crank. Let's derive the system. Differentiate the guess, yp prime equals u1 times y1 prime plus u2 times y2 prime, plus the group u1 prime times y1 plus u2 prime times y2. But that last group is exactly the extra condition we imposed, so it is 0 and drops out. That is the whole point of the condition. It keeps the first derivative clean. Differentiate one more time and substitute into the equation written in standard form y double prime plus py prime plus qy equals g, where the leading coefficient is 1. Because y1 and y2 each solve the homogeneous equation, every term that does not involve a derivative of u cancels completely. What survives is u1 prime times y1 prime plus u2 prime times y2 prime equals g. Put that beside our extra condition and we have a clean system of two linear equations and the two unknowns, u1 prime and u2 prime. The top equation has the functions themselves, the bottom has their derivatives and the forcing. Now we just solve it. Solve the 2x2 system with Cramer's rule. The denominator that appears is the determinant of the coefficient matrix, the matrix whose rows are y1, y2 on top and y1 prime, y2 prime below. That determinant is the Wronskian, written w, and it equals y1 times y2 prime minus y2 times y1 prime. Because y1 and y2 are independent solutions, the Wronskian is never 0, so we can always divide by it. Cramer's rule then gives u1 prime equals minus y2 times g over the Wronskian, and u2 prime equals y1 times g over the Wronskian. Finally, integrate each of these to recover u1 and u2, and assemble the particular solution as u1 times y1 plus u2 times y2. Putting it all together gives the master formula. The particular solution equals minus y1 times the integral of y2 times g over the Wronskian, plus y2 times the integral of y1 times g over the Wronskian. Two known solutions, one determinant, two integrals, and you have your answer for any forcing term. Let's pause on the Wronskian itself because it is doing real work here. It is the determinant with y1 and y2 across the top and their derivatives across the bottom equal to y1 times y2 prime minus y2 times y1 prime. What does it measure? Independence. If the Wronskian is identically 0 on an interval, the two functions are dependent. One is just a constant multiple of the other, and they do not form a real basis. If it is non-zero, they are genuinely independent. There is a beautiful result called Abel's identity, which says that for a second-order linear equation, the Wronskian equals its value at one point times an exponential of the integral of the coefficient p. The exponential is never zero, so the Wronskian is either always zero or never zero. It cannot flip in between. That is exactly why our formulas are safe, since y1 and y2 are independent solutions. The Wronskian is never zero, and we can divide by it everywhere without fear. Here is the conceptual leap in one picture. In the top panel is the homogeneous solution, c1 times y1 plus c2 times y2. The two coefficients are drawn as dials, locked at fixed settings. They are constants, they never move. In the bottom panel is the same combination, but now the dials have come alive. Instead of fixed numbers, the coefficients are wavy curves, u1 of x and u2 of x, turning as you slide along the x-axis. That is the entire idea of the method, captured in the name variation of parameters. We take the parameters that were constant in the homogeneous solution and we let them vary as functions of x. By choosing how they vary, we can make the combination satisfy the driven equation instead of the homogeneous one. The Wronskian and the integrals are just the bookkeeping that tells us exactly how the dials must turn. Before an example, let's settle when to use which method, because you now have two. Undetermined coefficients works by guessing a form, so it only applies when the forcing is a polynomial, an exponential, a sine, or a cosine. But when it applies, it is pure algebra, and it is fast. Variation of parameters always sets up for any continuous forcing term, but it costs you integrals, and those integrals can be unpleasant. So the rule of thumb is simple. If the forcing term is one of the nice, guessable shapes, use undetermined coefficients. There is no reason to compute integrals when a quick guess will do. But if the forcing is anything else, a secant, a tangent, a logarithm, a 1 over x, undetermined coefficients has no guess to offer, and variation of parameters is your only option. In short, guessable forcing, guess, everything else, vary the parameters. They are partners, not rivals. Here is that decision as a flowchart you can keep in your head. Start at the forcing term, g of x. Ask one question, is it a polynomial, an exponential, a sine, or a cosine? If yes, follow the branch to undetermined coefficients, because guessing will be the fastest path. If no, if the forcing is a secant, a tangent, a logarithm, or any of the endless functions that do not keep their shape under differentiation, follow the other branch to variation of parameters, which always works. That single question routes you correctly almost every time. The only subtlety is that even for a guessable forcing term, you may still choose variation of parameters if you happen to prefer integrating to guessing. It will give the same answer. But undetermined coefficients can never reach the functions on the right branch, so for those, variation of parameters is not a preference, it is a necessity. Let's solve one that undetermined coefficients simply cannot touch. Y double prime plus y equals secant x. There is no shape to guess for a secant, so variation of parameters is the only way in. First, the homogeneous solutions. The characteristic equation is r squared plus 1 equals 0, with roots plus and minus I, so y1 is cosine x and y2 is sine x. Now the Wronskian, the determinant with cosine x and sine x on top, and their derivatives negative sine x and cosine x below. That works out to cosine squared x plus sine squared x, which is just 1, a very friendly Wronskian. Our forcing g is secant x. Plug into the formulas. u1 prime is minus y2 times g over w, which is minus sine x times secant x, and since secant is 1 over cosine, that simplifies to minus tangent x. And u2 prime is y1 times g over w, which is cosine x times secant x equal to 1. Integrate u1 is the natural log of the absolute value of cosine x, and u2 is simply x. Now assemble the particular solution. It is u1 times y1 plus u2 times y2, which is cosine x times the natural log of the absolute value of cosine x plus x times sine x. So the full general solution is the homogeneous part, c1 cosine x plus c2 sine x, added to that particular solution, cosine x times the log of the absolute value of cosine x plus x sine x. Take a moment to look at the form of this answer. One piece is a cosine multiplied by a logarithm, the other is x times a sine, an oscillation whose amplitude grows. Neither of those is a polynomial, an exponential, or a plane sinusoid. There was no possible guess in the undetermined coefficients table that could ever have produced them. That is the whole reason variation of parameters exists. The forcing term reached outside the guessable families, and the method followed it there, returning an exact closed-form answer built from a logarithm and a growing oscillation. Here is a second tangent example to show how the integrals do the real work. Solve y double prime plus y equals tangent x. The homogeneous solutions and the Wronskian are the same as before. y1 is cosine x, y2 is sine x, and the Wronskian is 1. Now g is tangent x. So u1 prime is minus sine x times tangent x, which is minus sine squared x over cosine x. Rewrite sine squared as 1 minus cosine squared, and that whole thing simplifies to cosine x minus secant x, a form we can actually integrate. And u2 prime is cosine x times tangent x, which is just sine x. Integrate each. u1 becomes sine x minus the log of the absolute value of secant x plus tangent x, using the standard secant integral. u2 becomes negative cosine x. Assemble u1 times cosine x plus u2 times sine x, and after the sine x times cosine x terms cancel, the particular solution is negative cosine x times the log of the absolute value of secant x plus tangent x. The integrals carried all the difficulty exactly as expected. Here is where variation of parameters truly outclasses undetermined coefficients. It works even when the coefficients are not constant. Undetermined coefficients is built entirely for constant coefficient equations, but variation of parameters only needs the two homogeneous solutions, however you got them. Take x squared y double prime minus 2xy prime plus 2y equals x cubed, an Euler equation, with homogeneous solutions y1 equals x and y2 equals x squared. First, standard form, divide everything by x squared. This is critical. The forcing term g becomes x, not x cubed, because dividing the right-hand side by x squared turns x cubed into x. The Wronskian is x times 2x minus x squared times 1, which is x squared. Then u1 prime is minus x and u2 prime is 1. Integrate, u1 is minus 1/2 x squared, u2 is x. Assemble, and the particular solution is 1/2 x cubed. Notice no constant coefficients appeared anywhere, yet the method sailed through. That generality is its real strength. A little history, and it is a beautiful one. The trick of letting a constant vary was first used by Leonhard Euler in the 1740s, while he was studying how a planet's orbit drifts under the gravitational tug of the other planets. The constants that describe a perfect orbit slowly change over time, so Euler let them become functions. In the 1770s and 80s, Joseph Louis Lagrange took that idea and forged it into the general method of variation of parameters for linear differential equations, again in the service of celestial mechanics. So this method was quite literally born from the heavens. The Wronskian, the determinant at the center of the formulas, is named for the Polish mathematician Józef Wronski in the early 1800s. Its refusal to vanish is precisely the certificate that your two solutions are genuinely independent. A computation about drifting planets became the universal tool for forced linear equations. Let's recap. Variation of parameters seeks a particular solution of the form u1 times y1 plus u2 times y2, where u1 and u2 are now functions rather than constants. Before you start, put the equation in standard form by dividing so the leading coefficient is 1, and read off the forcing term g from the right-hand side. Compute the Wronskian, the determinant y1 times y2 prime minus y2 times y1 prime, which is never 0 for independent solutions. Then apply the formulas. The particular solution equals minus y1 times the integral of y2 times g over the Wronskian, plus y2 times the integral of y1 times g over the Wronskian. This method works for any continuous forcing term and is required whenever the forcing is something like secant x or tangent x. For the nice guessable forcing terms, undetermined coefficients is faster, so save variation of parameters for when nothing else will do. Next episode, our solving toolkit is finally complete, and we aim it at real physical systems, mechanical and electrical vibrations. Today we built the method that never fails, variation of parameters. Start from the two independent homogeneous solutions, y1 and y2. Undetermined coefficients combines them with constants, but here we let the constants vary. We look for a particular solution of the form u1 times y1 plus u2 times y2, where u1 and u2 are now unknown functions of x. Imposing the equation, plus 1 can be an extra condition, gives two algebraic equations for the derivatives u1 prime and u2 prime, and solving them brings in the Wronskian, the determinant y1 times y2 prime minus y2 times y1 prime. The result is a pair of formulas. The particular solution, yp equals minus y1 times the integral of y2 times g over the Wronskian, plus y2 times the integral of y1 times g over the Wronskian. Here, g is the forcing term after you divide the equation so the leading coefficient is 1. Use undetermined coefficients when the forcing is a polynomial, exponential, sine, or cosine, because guessing is faster. Reach for variation of parameters when the forcing is anything else, like secant x or tangent x, where no guess exists. Next episode, we turn this complete toolkit on real vibrations. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.